Okay, so I found something pretty weird in the tiling data set. Basically, it turns out that higher values for output bounds and kernel bounds basically lead to higher runtimes. That's kind of what I found. And then based on that observation, I trained a linear regression model which just took in the config features and then submitted it. And we've got a public score of 0.64, which is significantly better than random. In fact, I think at this stage we're sitting at we're sitting around 400th place. These notebooks are available to you. You can look at it yourself. You can come to whatever conclusions you want. But I'm just going to go through, the analysis that I did and the path that I took to get to 490th place using linear regression. Turns out you don't need the graphs. The graphs aren't important. You just need like 3 features. And that's all you need to predict tiling. Okay, so to start with, we're just going to look at the observation, and then you can judge for yourself whether or not I've come to the right conclusion or not. It seems like high values for node config variables lead to faster runtimes. Or being a bit more specific, the fast runtimes always have high values for the variables. So what are the variables? Well, remember that the config features, there's like 24 different features, and each one represents what is the maximum size that we can allow a tensor to be when we're processing that tensor for a given dimension. So the maximum size for the 0th dimension is given here by kernel bound 0. And this is for the kernel of the node. And then the maximum size for kernel bounds 1 is given here. If you need more of an explanation about what the hell I'm talking about with this tiling thing, I've got 2 videos already that you can watch. High values for these bounds variables seems to be related to faster runtimes. And that's the case with the kernel and the output, but not so much the input, which is kind of odd. That seems kind of strange to me. It all seems kind of strange. Okay, so like I'm making this big claim, right? High values means faster. It's kind of weird. Let's see if I've actually substantiated that properly. So please, have a think about this, and if I'm wrong, please tell me about it. It seems kind of more weird. This seems too strong, this correlation. Okay, so get dependencies. Let's have a look at the graphs. The first 10. Okay, these are normal graphs. We're at the tiling database, not the layout database. Okay, and we'll just pick the 4th graph. And we'll just look at the variables. Again, normal 6 variables. It looks like we've got 1,379 trials. And again, you get your config feat. 24 variables per trial. That's like normal. We've got 106 nodes in the graph. Okay, so what we're going to do is we're going to get the runtimes by normalizing the runtimes that have been given to us. We're going to get some sorted indices so that we're going to, so that we know which are the fastest runtimes, which are the slower runtimes. And then we're going to sort the configs and the runtimes by fastest runtime first. Right? So that's all we're doing. We're just taking all the trials and sorting them such that we have a new list, and the fastest runtime and the fastest config for each trial is in the bottom of the list. And just to make sure that we've done this right, we're just going to plot it, right? Plot. Yeah. And what we should see here is it'll just be a graph going up, because every runtime is faster than the one before it. It's slower than the one before it, right? There's more seconds elapsed or whatever. Okay, great. So that seems to make sense, right? So it's like the y-axis is the runtime and the x-axis is the trial index. Okay, so the slowest one's around 60 seconds, the fastest one is super fast. Okay, cool. So we've now sorted the runtimes, and now the configs are also sorted as well. So having done this, we're going to do kind of a bit of a complicated plotting exercise. And what we're going to do is, for every variable, for every config variable, all 24 of them, we're going to plot the value of that variable relative to the other values of that variable for this graph as a dot. So the more yellow the dot, the higher the value relative to the normal values that you get. So for instance, at the input bounds product variable, which, it's just it's the last variable here, great. for that variable, for presumably like the first config of them all, which looks like it's this one. We've plotted the value, and the value is represented by the color. More yellow means higher, more purple means lower. So it looks like basically all the values are kind of sitting in the middle range relative to each other. So presumably there are like some outliers way to the side or something, but basically they're all green for this input bounds product, for this graph. Hopefully that makes sense. You can read the code if you want to get some more sense out of it. But yeah, so we plotted every trial for input bounds product, and these are the values that we see. They're all green. A lot of them are all brown or purple, sorry, which means that presumably they're all zeros. Let's just test that assumption. So apparently 22 input bounds sum is basically always 0. Let's just confirm that. That should, yeah, great. And then if we look at it, okay, it looks like it's all zeros, and let's just like sum it to see how many. Yeah, it's all zeros. Okay, that's what you'd expect. And this seems to say that 19 is also zeros. So let's just check that out. Okay, and then I'm imagining 23, mostly it's zeros or ones or something. The sum is, oh, it's also 0. Okay, so for some reason 23 has been plotted as green, but in fact 23 is also all brown. And that kind of, I guess that kind of makes little sense, because the point is it's all homogeneous color. There's no variation. That's the point. So no variation for a long time until, okay, now we get down to 15. It looks like there is kind of some variation here. A lot of purple on this end, a lot of yellow on this end. And that's kind of a bit weird, because it means that like the trials where the value is high are pretty fast, and the trials where the value is not high are like slow. You can kind of see it like sort of transition slowly from green to purple. And that's kind of like, that seems interesting, right? That seems like something we could use to make predictions based on. And weirdly, very strangely, every single variable, at least for this graph, seems to follow that pattern, where the very highest values are always the ones with the fastest runtime. Okay, and that's really wacky. That seems like a really strange thing. I assume that I'd done some weird error in the sorting, but if you look at the sorting logic, it's really, really simple. So that's really strange. And of course, the first thing I thought was like, right, well, I guess that's just like one graph. And then there are many graphs, and different graphs will act differently. So let's just randomly select a different graph, and we'll do the same plotting exercise. Let's get rid of this. Don't want that. Okay, so this one has a lot fewer trials. Yeah, 263. Again, we've got like lack of variation for all these variables. Okay, this time we've got a little bit different for 14 and 15. It looks like the yellows, the highest values, are not the fastest. But, okay, then again, when we get to output bounds 3, again, we see the yellows are the ones at the very bottom. This one, not so much, actually. Again, bit strange, right? This honestly seems like a super strong correlation that's a bit weird. So let's try another random graph to see, let's just, I don't know, 4,000. Okay, lots of trials this time. Nothing. And then again, for output bounds 3, we see exactly the same pattern. And then it's really strong for kernel bounds product and kernel bounds sum, right? Look at this. This is crazy. So I saw this and I assumed I was going crazy. I was going insane. So I thought, right, well, let's actually just check the correlations. And I made a little bit of code to just load every graph, grab all the runtimes, and then take the feature 14, which is output bounds sum in this case, and then plot the correlation of output bounds sum with the runtime, and append it to this array. So what's the correlation between the runtime and the sum of given bound dimensions, right? And weirdly, you get a super strong correlation. So this is the graph, this is the histogram showing all the correlations for all the different trials. And usually when you're doing machine learning, there are no correlations. Nothing is correlated with anything else, and you have nothing to go on. And no matter how much data exploration you do, you don't find anything. But look at this, right? You'd expect these to be distributed around 0, most of them having no correlation between the bloody sum of dimension bounds and the runtime. But look at this. there's like a huge cluster between negative 2.5 and negative 0.25 and negative 0.5. So there's like this very strong relationship between high values for the sum of input bounds for the kernel. No, wait, the sum of input bounds for the output. No, the sum of bounds for the output and low runtimes. There's this very strong correlation. But like, let's try a different feature. This one seems to be the strongest here. Feature number 2, which is just like the kernel bounds for the second dimension. Let's see what the correlation is there. So, okay, great. Here we go. Still, right? Super, super strong correlation, or at least there's like it seems like there's a lot of support for this negative correlation here, which like, that's honestly wild and crazy. If I've made a mistake, I really want to know about it, but I don't think I have. Maybe someone who knows a bit more about how tiling works can tell me why this would be, but it's pretty odd. Okay, so that's pretty weird. That's really strange. If we're right, we should be able to train a linear regression model that just looks at like a few features and completely ignores the graph, and that should get us significantly better than random predictions. And that's what I've done. It's in this notebook. We're getting a public score of 0.164, but I'm gonna go through the notebook now so that you can sort of understand what I've done, and maybe you can make like an improvement on it. Okay, so again, we just start by importing things, and then we select the indices of the variables that we're interested in. So 6, 7, 14, and 15, and in this case, what we've chosen is the kernel bounds sum and the kernel bounds product, and the output bounds sum and the output bounds product. I did like a very small number of experiments locally, just with the validation data set, and these 4 seemed like a pretty good bet, so that's what we're doing. Defining a nice function to load the data, so you give it files, it gives you x, which is like those input indices, and then y, which is the runtimes. And it just shapes them nicely so that they'll be able to fit into linear regression. Now there's the slowdown function, which calculates the metric that you can see from this competition. So overview, the guys describe this evaluation metric that you're supposed to use. So we've just copied that evaluation metric. Essentially, higher scores are better, with 1 being like a perfect score. So we'll just define those functions and define some nice like constants. Okay, so now we'll seed them. These are all the train files just sitting in the directory. These are the validation files. We load the data, just the train data, and then we create a linear regression instance just from like normal ass scikit learn linear regression, and then we fit it. And that's all we do. And then we'll just show the model coefficients, right? Because it's going to be like a multiplication coefficient for every variable. Okay, so then we make a prediction. Oh yeah. And so now, so the next thing we want to do is work out how good is the linear regression compared to like some baselines. So, okay, we get a mean squared error based on the difference between y, which is the actual train ground truth, and the predictions of the model on the train data set. That gives us like a train mean squared error. And we're using mean squared error instead of the competition metric just because like it's a good rule of thumb, right? We want to train this model to be able to predict the runtime based on the variables we're giving it. And if it's able to do that correctly, it ought to get a lower mean squared error. So mean squared error is like, it's like a thumb to the wind kind of test. Okay, so these are the model coefficients. They're all negative for the first 3 and positive for the last one. That's kind of weird. I thought they would have all been negative, just based on those like strong negative correlations we were seeing before. And it's got the intercept. Okay, so the model's been trained. Now we're just going to work out how good it is. So we'll find out the mean squared error on the train set. Then we'll load the validation data and see how well it does in the validation set. Presumably it'll be like worse on the validation set. And then we'll just get like a baseline to compare it to on the validation set, which is we're just going to keep predicting the mean of the validation set and see if our model is better than this like very basic uniform mean model. And if it's worse than the mean model, then obviously we haven't done any good and our model is like very bad. Okay, so the mean squared error on the train set was 0.64. The validation mean squared error was 0.63, and then the mean squared error for the mean prediction was 0.65. So we're doing a little bit better than the mean prediction, which is I guess that sort of implies that we're doing a bit better than random, but probably not a huge amount better than random because these numbers are pretty close to each other. Okay, so now what we're going to do is we're going to try to get the actual evaluation metric, the speed score, the slowdown score, and we're going to get that metric for our model that we've just trained, and we're also going to get it, we're going to print the perfect score under the metric, and then we're going to print the score if we just randomly made predictions completely at random. So, okay, for every file name in the validation file names, we get the runtime. We sort the runtimes by their length, and this means like this is like the perfect order. This is like the perfect ordering. Yeah, these indices are the perfect ordering, and then we get a speed score when you give it the actual runtimes in the perfect ordering, and we should get like all ones. These should be like all perfect. Then we shuffle those predictions, those indices. We shuffle them randomly, and then we predict again with these random predictions. Great. And then finally, we actually get the model to predict some runtimes, and then we get indices based on those runtimes, the predicted runtimes. Obviously, like these have nothing to do with the actual runtimes. These are just like our best estimate. And then we get a speed score for those predicted indices. And what do we have? Okay, perfect index, that's 1, that's what expected. Random score is like 0.15, and linear score is 0.26. So to me, that looks like we've done a fair bit better than random, which is great. Especially considering this competition is supposed to be all about like parsing graphs and understanding graphs. We haven't done that. We haven't bothered with that at all. We're just taking like 4 variables from the config of each trial, and we're making a prediction based on that. Okay, so that's all good. Now we're loading the sample submission file so that later on we can make some actual sample submissions of our own. We're retraining the linear regression model on all the data, because obviously before we just took in the trained data and trained it on that, and then predicted based on the validation to see if our model's any good. But now we'll train it on both the training and the validation data. And yeah, we'll print the coefficients again to just for curiosity. And then finally, what we're going to do is we're going to generate an ordering. We're going to generate a new submission file and then save the submission file, and then we'll submit that to the leaderboard. Okay, so that's what we've done. You know, you can go and read all of this yourself, but the basic gist of it is that boom, 0.164. No graphs needed, just some linear regression. I would honestly love for someone who knows a bit more about the subject matter to tell me what the hell's going on here, because that just seems like a very surprising amount of score you can get without using any kind of neural network at all, literally by just doing linear regression on 4 variables. I guess the only possibility maybe is that like this is not a very significant difference. Like this is actually just about as good as a random score. I think other people have maybe done a random baseline. So just what we're going to do to just be like completely certain is we're going to do another random baseline and submit it, and just confirm that other random baseline isn't somehow like way better. So we're just going to change the seed in this kernel, and we're going to save it, and yeah, we're just gonna submit the output again, and presumably our prediction is that it'll be around 0.111. Okay, great. So 0.108. It looks like random baselines are significantly worse than our linear regression that we're doing, which is cool on the one hand, but also kind of a bit weird on the other hand. A bit weird and a bit frightening. I don't know what's going on. So if someone can maybe like make a fork of this notebook and do some work out what the hell's happening here and why we're getting these weird like high values for the low runtimes, what the hell's going on there, that would be sick. That would be very sick. Please do that.